I'm showing you an activity. This is a coil and I have connected few LEDs with it, and see, this LED is lighted. So it's a coil and then these bulbs are connected to the coil. Now I bring another coil. This is a coil not connected to any cell or battery, but an LED is there. So if I move it closer, see now. I'm just bringing it closer to it. There is still some distance. So this is what we call as mutual induction. Now the magnetic flux through it is changing. When I bring it closer, the magnetic flux associated with it also changes, and this induces current in the secondary coil, and due to which this bulb is lighted. So we have seen in this activity that there are two coils. One was connected to an AC source, and I brought another coil connected to a bulb. So I can name them coil 1 and 2. So only one is connected to the source, second is not connected to any battery or source. It has only a light bulb, but it lights up when you bring this coil 2 close to the coil 1. This phenomena is called mutual induction. Reason we have already discussed. Now what is happening here? The current in this coil produces some magnetic field here too, and since we are using AC, so the magnetic flux with the other coil will also change. Let me take a simpler version of it. This coil, let me call it primary, which is connected to the source, and here it is connected to where I used a bulb. So when the current is flowing through it, the flux associated with it is also changing, induced EMF is produced, and this is closed, so current starts flowing. If I use a DC source here, then what will happen? When DC is passing through it, again there is a magnetic field. This magnetic field will pass through it, and there is a field associated with it. But will the bulb light up or not? Actually, we have discussed so far that a current is produced or EMF is induced whenever the flux is changing. In case of DC, the current flowing here is constant. So there is no change as such in the flux passing through it. So magnetic flux is there, but magnetic flux will not ensure that there is EMF or there is current or not. It is the change in flux which is important. So if I use DC, so the moment I switch it on, the flux takes some finite value from 0, so the flux is changing. So there will be a light in the bulb momentarily. Same way, if we switch it off, again the bulb will light up. So it will light up only when we switch on or we switch off in case of DC. But AC, it is changing continuously. So the flux is changing continuously. That's why there is a flux change in flux. So flux for secondary here is depending on the current in primary. I'm taking this as current in this as primary and this as secondary coil. Flux of this is depending on the current flowing here. And this constant of proportionality here is called the coefficient of mutual induction or mutual inductance. It is measured in Henry, name of a scientist, measured in Henry, SI unit of measurement of this. And it will depend on coefficient of self-inductance we discussed. It depends on the geometry and the medium. Coefficient of mutual induction will depend on geometry, it will also depend on the medium, but apart from it, it will also depend how close these two coils are and what is the placement of these. For example, if we have this as the primary, the secondary may be kept like this, it may be kept like this, or there may be some other orientation. In all these cases, the mutual inductance will be different. It will be maximum here. See, the EMF or the current is depending on how much flux is changing. So if the changes are large, there will be more induced EMF. If changes are less, there will be less induced EMF. And how much flux is passing through it, how many magnetic field lines are passing, that will depend how the secondary is placed. If the secondary is far away from the primary, then maybe the changes in the primary may not affect the flux passing through the secondary, or the flux passing through the secondary may have a negligible value. So there won't be any induced EMF. So mutual inductance will depend on the distance and how are the coils placed. That will depend on that. We can take it in terms of induced EMF also. Induced EMF in secondary is depending on the rate at which the current is changing in the primary, not on the current, on the rate. And here the constant, or we can use simply dip by dt into a constant of proportionality, which is called the coefficient of mutual induction or mutual inductance. And we can take this expression from here also. Faraday's laws. So minus d by dt, flux for secondary. So if this is for n turns, if we have for one turn, if we have n turns, we can multiply it by n phi can be written as MIP. M is not depending on time, so it is M dip by dt. Same as this. How can we define this? Is secondary. So coefficient of mutual induction is numerically equal to the induced EMF in secondary when the current in the primary is changing at the rate of 1 ampere per second. This is how we can define the coefficient. So again, briefly telling you, there are two coils, primary and secondary. We have connected the source of current in primary. Flux will pass through the secondary also, but when this flux changes, there will be a current. If we use DC, there will be current only when we switch on the source or we switch off the source, because only then there is a change, otherwise constant current is flowing. Flux is constant. Constant flux will not give rise to any current. It is the change in flux which will produce the induced current. Okay, so when we have two coils, it is called mutual induction, because the current change in one induces the current in the other coil. Okay, now again, as we did for the self-inductance, we calculated the value of self-inductance for a solenoid. For a mutual induction, we will have two solenoids. So let me consider two solenoids, again very long solenoids, infinitely long solenoids, but I am taking, even if one is larger than the other, I am taking a common length L. Area of cross section, inner one, let me call it A1, outer one, let us take it A2, length is L, and once I will take the inner one as primary, outer one as secondary, then in the other one I will just reverse this. Okay. Let me take case 1. Inner is primary. and outer one is secondary. So it means current is passing through this inner one. It has current, say I1, and we have to find out the induced EMF in the secondary coil. Okay. So secondary means we are taking outer. N2 phi 2 is equal to M current in primary. The inner one I am writing 1, and for outer one I am writing 2. Okay. So N2 phi 2. Now see, when the current is passing through the inner solenoid, and we have taken infinitely long solenoids. For an infinitely long solenoid, there is no magnetic field outside, and inside we take it as uniform. Now imagine the situation. Suppose these are the field lines passing through it, and outside the field is 0. Between the two solenoids, the field is 0 if we have taken current in the inner one. So it means the flux for each turn of secondary is actually same as flux for the inner one, because there are no lines, no magnetic field lines between the two. So phi 2 I can write it just phi 1. It's very important point. N2. Now phi is B into A. So B1 A1. B1 is the magnetic field, mu naught N I. I1 gets cancelled, we get M as mu naught N1 N2 A1 upon N. This is when I am taking inner one as the primary. So one point that is to be kept in mind, if the inner is primary, there is no field outside, so flux for the outer one same as the flux for the inner one. Okay. Now let's take the second case. Now outer one is the primary. So the source of current will be connected to the outer solenoid. In that case, now what is the flux? We have to find out now for the inner one. Let us call it M dash I2. So current is flowing in the outer one. I want the flux for the inner one. N1. Now this time, there are magnetic field lines throughout. But I want only the flux for the inner one. So how will we calculate? We will take whatever is the field present here into the area. This one. I need flux only for this one. Flux is B into A. So whatever magnetic field is there multiplied by this area. Now field is due to this. What is the field here? It is mu naught N I. The field is due to 2 actually. So N1, B2 is mu naught N2 I2. A1 is equal to M dash I2. So what is M dash? Mu naught N1 N2 A1 upon A. And see what is the relation between the two. We have considered same length, L. This is common length, okay. Inner, whether we take the inner as the primary one or we take outer one as the primary one, the coefficient of mutual inductance is coming out to be same. It means same EMF will be produced if the rate of change of current is same. So that's all. Coefficient of mutual inductance, we have calculated this value for a pair of solenoids. We have a device which works on this principle, that is transformer. You have two coils, one is called primary, another one is called secondary, and then we will see how does it work. The source of current will be there in the primary and we will take the output from the secondary. The advantage is that we can step up or step down it. Say for example, if we have 10 volt, we can make it 20 or we can make it even 5. So we can lower the voltage, we can increase the voltage depending on the requirement. So that's the use of transformer, will be taken in some other class. Thank you.